Hello, everyone. First, I'd like to thank the organizers for the invitation and opportunity to speak here with you all today. When I was first invited to speak in this session, I knew I wanted to give a talk about giving talks, but I had to pause for a while and think about what is a good means to do that, especially non-interactively as a not only remote, but asynchronous talk such as this. So what I'm going to do today is I'm going to share some of my experience over the last couple of years. I've given a variety of outreach and expository talks at the grade school level, at the high school level, at the undergraduate level, and to adult non-mathematicians. I won't talk about all of them today, but I'll give a couple examples, particularly from the younger grades in this talk. But I'll do so hopefully in the structure of explaining how I think about planning a talk. Because one thing that has really changed for me over the years is at first I thought that planning a talk for kindergartners or planning a talk for high schoolers or planning a talk for a popular adult but non-mathematician audience would look very different. And the majority of my planning now actually doesn't look very different. So I want to talk about the way that I set things up, and then I'll give two and start a third example. So say we're giving a talk not in a research seminar. That is, our goal is not to teach people a new specific piece of mathematics built on top of a lot of mathematics they already know, but rather to introduce them to some mathematics, whether it's a new topic or a surprising result, or a new way of thinking about something. But the context I have in mind is that this is outside of their normal professional lives. They're not mathematicians. And the way I start planning is I will write down for myself what I want the theme of the talk to be. That is, what general branch of mathematics I want to be talking about. And then I will try and set two different learning goals for the talk. I want to set a goal for what I want people to be excited about and learning during the talk. That is, while things are fresh in their mind, while I'm in the midst of explaining things and all of the pieces are there for them to grab, what should they learn right then? Even if they're not going to remember it later, because this whole cloud of knowledge I just imparted on them is rather far from what they do normally. What's the aha moments going to be at the time? And then separately, and in my mind, the most important part in planning these sort of talks is I want to figure out, what do I want them to remember in a month? It doesn't need to be a fact, but what do I want to come out of this talk? What do I want their experience to be when they think back on when they went to some math talk? Yeah. So the example theme I want to talk about today is topological invariance, because I've given a couple talks in this general theme that we can reach out to. So like I said on the last slide, the thing that's important to me here is that the topic is rather general. Like, I did not pick that I'm going to talk about the volume of hyperbolic three manifolds, or that I am going to say talk about the third homotopy group of a manifold or something. And those two, it's pretty clear why I wouldn't talk about those. No one would have any idea what I'm talking about in a general talk. But the reason that I think it's a good idea to remain a little general, at least in this stage of the planning, is to not focus yourself on only explaining to people one facet of that topic of math. While to us topologists, we might think giving a talk, starting out saying, I'm going to give a talk on the fundamental group, sounds extremely general. There's so many things going on in the fundamental group. But if you think to a non-mathematician, that's an extremely specific topic. Like, you have to dive into what are topological spaces, what are invariants, what is this particular invariant, and why do we care? And that's a lot of baggage to have to develop in the means of making a talk. So keeping it very general at the beginning lets you maybe easier change your mind as you start planning the talk, what the scope is going to be. And the next thing I would do is once I've chosen that topic, I kind of make an idea web for myself of maybe secretly when I started thinking about the talk, I was like, I'm going to give them a talk about fundamental group. But I zoomed out and I let myself think, okay, well, I'm giving a popular talk. I'm going to talk about a topological invariant. That's one example. Let me start listing a bunch of other exciting topological invariants. And usually I'd probably even make a more complicated web than this, with more interconnections and stuff to just kind of get my mind ready to write the talk. I've listed here in white a bunch of things that I would think of as topological invariants. And I've also not shied away from mentioning in maybe other colors or highlighted somewhere, things that we might not think of as a topological invariant. Here in red, I wrote down some geometric invariants, and in yellow, I wrote down some numerical invariants, like the fact that numbers can be even or odd, or a way to tell two sets apart is their cardinality. These are things that to us might feel far away from topological invariants, but to someone who hasn't thought about invariants at all, might seem extremely close. So they're good things to keep for me to keep in mind when I'm planning a talk at this stage. And I guess I should also say this is probably obvious from the nature of this talk. I am just giving you a bunch of my opinions on how to write a talk. Like, I have no authority on why this is the way to do things, only that doing this helps me out. So yeah, so take it with that in mind. And I guess I thought to mention that disclaimer right now, because the next thing I'm going to say is something that I think is a bad idea to do, particularly in expository talks or talks to more general audiences. And again, the examples I'm going to give are from grade school and high school. So keep that in mind as well. But it's something hard because for a mathematician, it's really tempting to give a talk about a definition. I'm going to talk about topological invariance. How could I possibly start a talk about topological invariance without telling you what a topological invariant is? That's the natural way to start. How do I do that? Well, I'd say, well, a topological invariant is something that is assigned to topological spaces that is invariant. And that's not going to be very helpful to people, no matter how you try and make that definition palatable or whatever. It's not going to be very helpful if you haven't seen topological invariance already. And again, this is not just obviously about topological invariance, but about any topic in math. Think about that. When trying to introduce that topic, it's only helpful to give the definition precisely if the audience kind of already knows what that topic is. And going with our example, how did we learn about topological invariance to start with? Well, we learned about things like connectedness and genus. And then we found that these specific examples are all types of topological invariants coming from well-known ones. And so if your audience doesn't know about connectedness, doesn't know about genus, doesn't know about the fundamental examples, maybe the overarching definition is not a helpful way to start. Okay, so that's my goal. How I would start, build a web. How I would not start, lay down a definition. And so what I want to do next is explain two examples of talks in this area that I've given. The first specific example here, my target audience was I was speaking to grade schoolers about mathematics. And my math goal at the time was more specific, but it fit into this topological invariance. I wanted to explain something about Betty numbers, something about homology. I guess the more general way to phrase this goal is I wanted to explain something about invariance of surfaces. And the particular invariant that I was honing in on was I wanted to explain some of the lower Betty numbers to them. So that was the goal, invariance of surfaces. What do I want them to remember in a month? Well, I want these grade school students to remember that in mathematics, there's different notions of being the same. That's kind of the first thing you need to know to talk about invariance, that you could have things that appear different but are the same. You have to make precise what you mean by the same, and it differs by context. So I want them to know that. I want to have some way of really imparting that on them. If there's one takeaway from the talk, if they forget everything I liked about connectedness or about Betty numbers, that's fine. If they remember this notion, that's what I want. And maybe as a secondary goal for Remember in 1 month would be, for the students who really liked the talk, maybe, that we can use numbers to summarize properties and easily compare shapes. That numbers are not just the topic of study in math. That's something that a lot of grade school students know, but numbers are something that we can use in math to summarize other data that didn't appear mathematical to start with. So this is more or less the outline I started with when planning the talk, and I want to share a little bit just where I went with it from here. So having a group of around 20 or so grade school students, I think they were like 4th graders, 5th graders. I first, to try and get around this point that there's different notions of the same, and that's the first thing we would need to decide on to even talk about something like this, I had them group up with their friends in triples or quadruples or whatever, small groups, and take out a sheet of paper, take out 2 sheets of paper, and on one sheet, draw a bunch of shapes that are the same. And on the other sheet, draw a bunch of shapes that are different. And then I had them trade the sheets of paper that were the same shapes with one of the other groups, and had that group then try and explain what was the same about all the shapes that were drawn on that sheet of paper. Did they have the same number of corners? Did they have the same area? Did they have the same perimeter? And we looked for all the shapes. Anyone looking at any of the sheets that had the same shapes on it, everyone agreed the shapes were the same. But we realized when we tried to make precise what we meant by the same, that not all of our definitions worked for everybody. Namely, some groups, I guess to say it more mathematically, some groups drew shapes that were congruent and some groups drew shapes that were similar. But everybody seemed to agree that the number of corners was a definite invariant. No matter what we were talking about, triangles were never the same as squares, and squares were never the same as pentagons. Our individual rules for making 2 triangles the same differed between groups, but that bigger invariant was shared by everybody. So we use this as a jumping off point to explain that mathematicians might look at the same collection of shapes, and depending on how fine they want to pay attention to the details, agree or disagree on if the 2 shapes are the same. Just like one of the groups thought that like similarity as a superset of congruence was the correct relation, and the other group thought that it was congruence. And so we talked about making this even weaker, and talked about the idea of connectedness. So saying, well, who cares about corners? Maybe that's the next move. If we allowed ourselves to smooth out corners or ignore corners, then actually all the shapes that you drew, even on the sheets of paper that were considered different, would all be the same. They'd all just be 1 loop. But a shape that would be different would be 2 loops or 3 loops, or a line would be different than any of the polygon loops that had been drawn. So to get from there to surfaces, the next thing I wanted to do, since remember, that's my goal. I want to explain to them something about surfaces. A lot of people have seen polygons before. They've thought about polygons in terms of math, but maybe haven't thought about surfaces. I was hoping that would be a fun place to take them. So the next thing we did was I drew a sphere and a donut on the board. And we talked about, as a class, why those 2 shapes that are obviously different should be different. How could we tell that they are different from? So there was a bunch of fun ideas on what makes a sphere different than a plane, but a lot of things that were hard to make precise. So gave the class a hint. I knew what answer I wanted them to come up with, and it wasn't quite working. But the hint was to try and think about if you could cut the shape somehow, if you had scissors and you could cut it, what could we say about the different ways that you can cut the shape? And someone points out that, well, you can cut the donut into kind of like a cylinder, sort of a bagel-y shape. And a sphere you can just cut into like a little cap and like the rest of the sphere. The point is that you could cut a sphere, and no matter how you cut a sphere with a pair of scissors, you're always going to end up cutting it into two pieces if you cut a closed curve on a sphere. But if you do that on a donut, that's not necessarily true. Some cuts on a donut, you can cut off a little cap of the donut, but other cuts on the donut, say going around one of the homology generators, don't disconnect the donut. They leave it connected. And so that was an invariant that we could try and start talking about for surfaces. We can call it the cutting number. And it's the number of different cuts like that you can make in a surface before the surface falls apart into pieces. And so we then drew a picture. We ended by drawing a picture of a genus 2 surface and talking about, like, obviously that's not a sphere or a donut, but we can see from how hard it was to make precise the notion of a hole in a donut, it'd be hard to make that notion precise too. But we could try and figure out what the cutting number is. And of course we can't prove anything, but we can try and draw how many cuts can we make? Can we show that we can make more than 2 cuts without disconnecting it into pieces? So that was one idea for trying to talk about this in grade school. The second example I'll share with you is giving a talk to high school students, again about topological invariance, but here maybe the goal was to talk about the fundamental group instead. And the reason was I wanted to de-emphasize numerical invariance in this talk. A lot of times, or at least my memories of high school, were that there's lots and lots of numbers in math. And so I wanted to give a talk that de-emphasized the primacy of numbers and showed that other structures could be important. Of course, we can't exactly talk about a group. So the main thing I want people to remember a month from now is that the intrinsic properties of shapes can be detected from patterns, patterns that can arise by thinking about the surface itself, namely by keeping track of loops on the surface. And instead of giving this talk in a way that was more back and forth or collaborative, the way that the first one was, this I decided to still not do as a lecture, but do more as a story. So I told them I was gonna tell like a mathematical parable, and then we were gonna talk about it at the end and try and figure out how to tease out the real mathematics and see what we can use from the story. And so I'll only tell a very abridged version of the story here, but it goes like this. On a two-dimensional world somewhere, there was a very smart collection of ants. They developed ant trigonometry and ant geometry and ant calculus and lots and lots and lots of ant mathematics. And the smartest ant of them all was Antimodes, who was always talking about math, to the point that it annoyed all of the other ants. And they eventually banished him from their ant community because they were just sick of hearing about his ant calculus. So Antimodes goes on a walk. He's mad at them too. He wants to get as far away from them as possible. And so he starts walking directly away from the ant village. And he walks and walks and walks and walks and walks and never turns. But much to his surprise, at some point, he arrives back at the ant village where everybody's mad at him and tells him to go away. And he remarks, that's exactly what I did. I walked directly away from the village. And I never turned, and somehow I'm back here. And Antimodes is very confused because he's very good at ant geometry. And he knows that if he walks in a straight line directly away from the ant village, he should never return to the ant village. So Antimodes is very bothered by this, and he spends a lot of time thinking about it, trying to figure out how this could happen. And so here I ask the students like what they might think Antimodes might be thinking of, or what a solution to this paradox would be. And get the answer I wanted, which is that, well, maybe Antimodes lives on a sphere. And like, that's correct. Maybe he lives on an orange, like the whole ant society is going on an orange tree. He walked all the way around the world and he came back and he ran into his village again. And so Antimodes thinks of this, and he starts thinking a lot about three-dimensional geometry. Even though he can't see the world from the outside, he's living on this shape. But he realizes that that could happen. He could walk all the way around the world and come back if his world was shaped like a ball. But the real question that bothers Antimodes is this enough to conclude that I live on a sphere? I know that if I walk outwards, I come back to where I started. And I know that that's a property that happens on a sphere. But does that mean I live on a sphere? And he quickly realizes, no, it doesn't. The same thing could happen on a donut. If you lived on the surface of a donut and you walked all the way along a closed curve, you would come right back to where you started. So Antimodes is puzzled by this. He wants to find a way to figure out what the shape of his world is, even though he can't leave the surface and look at it from down above. And what Antimodes decides to do is to try and draw a map. He starts back at his village and he leaves it in lots and lots and lots of different directions. And he starts drawing a map of what he sees along his journey. Mathematically, of course, more or less what he's doing is he is looking at the pullback of his world along the exponential map from the tangent space onto the geometry if he's walking without turning. And of course, that's not exactly the story that I'm trying to tell here. We're trying to talk about like eventually the covering space transformations in the fundamental group, not this Riemannian geometry concept. But it works well enough for our story. For the main example, we're interested in the torus. The exponential map is a covering map. It is the normal covering map from the universal cover. So it'll work for us. So the goal is to draw a torus on the chalkboard and then try and draw the process of Antimodes making a map and try and get the students involved in trying to draw this. So we have maybe a village, maybe we have some trees, we put a couple markers on this three-dimensional like torus of revolution. And then we try and draw paths that Antimodes might have walked on the torus, and then draw his map where he thinks of that path as being a straight line because he never turned. And what we find is Antimodes, if he lived on a sphere, his map shows that if you walk a certain distance, namely pi, if you were on the unit sphere, you walk halfway around the, or 2 pi, sorry. You walk all the way around the sphere, the full circumference, you get back to where you started. And so no matter what direction you walk in, you always see your initial ant city at the center of your map and everywhere at a distance of 2 pi out. That's what you would see if you lived on a sphere. But we find out from trying very carefully to draw this map for the donut-shaped world that Antimodes gets a very different map. He actually finds a grid-like pattern in his map of ant cities. You could walk a closed loop along one generator of pi 1, get back. You could walk a closed loop along the other generator, get back to the city. That gives you 2 distinct locations of the city on your map, along the x-axis and on the y-axis. But you could also walk diagonally on a 1-1 curve, or along a 2-1 curve, or a 1-2 curve, or a PQ curve. And all of those will spiral around the donut a bunch of times and get back to the city exactly at the end of their journey. So Antimodes draws this, and he ends up drawing out his map showing a like integer lattice of ant cities in the plane. And while of course there's only one actual ant city, what his map has shown him is all of the different inequivalent ways that he could have walked and gotten back from his city back to his city by setting out in different directions. And he realizes that the pattern on his map, the pattern of cities, is an invariant that he can use. He can tell if he lives on an orange or if he lives on a donut by walking lots and lots and lots of paths and seeing what pattern shows up when he draws the map. So after that story, then the goal is to kind of back out and try and connect that to mathematics. So explain, draw a better picture of the covering map from, say, from the plane onto a cylinder, from a cylinder onto a torus, and explain how Antimodes' map is really that covering map. And maybe give a couple fun examples that you could say not so precisely of where these ideas come up in modern mathematics. Okay, so finally, I want to leave you with a third example in this same area to think about on your own, that I'm happy to talk to you about a way I've approached this in office hours or something, if you would like. So we'll stick with the topological invariance game. So your goal is to talk about the Euler characteristic, say. And your goal is to talk to a popular science general audience, so like a bunch of adults, but like non-mathematicians, non-math majors, may or may not like mathematics. And you do want them to remember something in a month. So I put here a suggestion of what I would want an audience like that to remember in a month. I don't care if they remember how to compute the Euler characteristic. They're a bunch of adults with other jobs who might not care if they can actually compute that. But what I do want them to remember is that math is full of hidden patterns that almost seem too good to be true until you discover them and they look inevitable. That math is full of patterns. That's what I want them to remember. So yeah, if you want to try this exercise, I encourage you to here pause the video for a second or for a while and think about what you would do in this direction. I'm not going to lay out a whole plan of what I've done in a situation like this, but the reason I'm asking you to pause now is I do want to share one really, really cool idea in this direction that I learned from actually from Alex Kontorovich on Twitter. So I don't want to spoil it. I would like you to think about this, but I do want to share the idea. So I will pause here and then great. So only continue if you want to then see the idea I'll leave you with. Here is an awesome idea of Alex. So plot a bunch of polyhedra. Take all the polyhedra you know, maybe all the Archimedean solids or more. They don't even have to be very regular. Plot them all in R3, where the coordinates of a polyhedron are its number of vertices on the x-axis, its number of edges on the y-axis, and its number of faces on the z-axis. Now, at first, all the polyhedra just seem like a jumble of shapes. People might not expect them to show any pattern when you do this seemingly arbitrary plotting in R3. But of course, we know they all lie on the plane v minus e plus f equals 2. And so when you just do this, you get a plane in R3, which even for people who don't like math, I feel like it's got to make you stop for at least a second and go, wait, what? And that's a possible in. That's an in that I took in giving a talk like this to try and hook people. So I really like this idea. And I just wanted to share. So yeah, so that's where I will end. Thank you all. And yeah, feel free to discuss ideas for that with me later on in office hours or something. Have a good one.